briefly introduce myself and as a speaker. So I'm Sicheng He, and I'm currently a postdoc associate at University of Michigan. I'm a co-organizer of this seminar series. Several rules about today's talk. I think you can, as Disha mentioned, you can leave your question in the comment during the talk, or you can wait till the end of the talk and ask your questions yourself. And this talk will be taped. So, also please turn off your camera to save some bandwidth for the speaker. With that, I would like to introduce our speaker for today. It's my pleasure to invite Dr. Wenchao Yang to give a talk today. Dr. Wenchao Yang is currently a postdoc fellow in the Department of Mechanical and Materials Engineering at Queen's University with Professor David Rival. He received a PhD degree from the Virginia Tech in engineering mechanics. His research interests cover a wide range of topics in experimental fluid mechanics, including complex flow in bio-inspired mechanics, vortex-induced vibrations, wake interference, and fluid structure interaction. He's currently focused on developing and implementing distributed pressure network to predict aerodynamic loads. With that, Wenchao, please start from here. So.
Okay, thank you, Dr. He, and thank you, Dr. Fan. And good morning, everyone. Today, I'm very glad to introduce our research progress on aerodynamic load estimates with sparse pressure data. So first, let me introduce some background. So as you can see from this video, and when the birds or some animals flying, so we can find there is complex changing of the geometries, and we can also imagine that the pressure distribution on the wings is also complex due to this complex geometries, and there is also some study on pressure distribution along wings in the acceleration and the takeoff flight process. As you can see, here is a wing of the one bird model. So you can see here are 5 pressure sensors on the wing. And during the acceleration and the takeoff flight, you can see a very large variation on the pressure distribution. For the downstroke, so the pressure distribution basically positive, but for the upstroke, the pressure distribution becomes negative. And during the acceleration, we can find very large pressure variation along the wing. So basically, many studies have confirmed that birds can actually sense small change in air pressure. In that case, they can just have some prediction for the storm in front of them, so they can prepare themselves for the storm. So we can inspired by this idea that maybe for the aircraft, it can also sense the surface pressure on the aircraft, and then it will benefit the flight control for the gust response or something else like the environmental flow. So basically, our idea is something like this. We want to get the mapping between the surface measurement and the measured aerodynamic loads. In this way, we can predict or estimate the aerodynamic load from the surface pressure measurement. So and this model can also provide some insight on how to optimize the sensor located on the aircraft and how many sensors we need to do this job. So basically, our research focus on this routine. So we care about the gust and any other environmental flow on the aircraft. And we get some major information from the surface pressure measurement. And we use those information to estimate the aerodynamic loads on the aircraft. So this is the basic idea of of our research. And so for our group, actually, we are developing 3 different approaches for the mapping between the sparse pressure measurement and the aerodynamic loads. Today, I will focus on the first 2 approach. One is a linear regression, and this part of job has been published in Physics of Fluids already. And another part of job is we want to get some neural network model for the dynamic separations on the aircraft. And finally, another approach is the transition network modeling. So this work will be introduced by the Frieder in May 2020. So basically today's talk, I will focus on the above 2 approach. So here are some open questions my talk may be attempt to answer. The first question is, can we actually predict aerodynamic loads from the sparse pressure measurements? And the second question is, how many sensors we need to accurately estimate the aerodynamic forces? And the final question is, what is the optimal placement of the pressure sensors? Okay, so already some research have focused on how to get reconstruction flow information from the sparse measurement. For example, for the Ericsson, they placed the sparse sensor on the surface of the circular cylinder, and they use this sparse measurement to reconstruct the flow structure for the flow past the circular cylinder. And for other researchers like Penn, so they also use some sparse measurement to predict the flow structure, but for this case, they focus on the 2D airfoil. Today, for our research, we basically focus on the dart wing, especially for the non-cylinder dart wing in this way. So for this dart wing, we have 16 pressure tapes on the dart wing. And the dart wing was 3D printed, and all the pressure channels are located inside the dart wing. So in this way, we get the information about the surface pressure on the dart wing, and we reconstruct aerodynamic loads from those pressure tapes. Okay, so today, basically first introduce our experimental setup, and then introduce our linear regression between the sparse pressure data and the aerodynamic loads. And then I will introduce some preliminary work on the neural network modeling for the dynamic separation. And finally, I will introduce some future plan about this research. Okay, for our experiment, so the experiment was conducted in a towing tank at Queen's University. So as shown here, so the model moves from right to the left, and we have a linear actuator to drive the vertical motion, and we have a traverse that can move in the streamwise direction. Here, we use the normalized distance to evaluate the motion of the dart wing. So we actually focus on 2 types of darts here. So one is the axial acceleration. So in this case, the dart wing starts the acceleration from some point, and after some distance, the acceleration becomes 0, and it continues to move to the end. But so another type of gust is a vertical gust. So we actually use a linear actuator to drive a vertical motion for the dart wing. And so for the Reynolds number during the experiment, it's from the 300,000 to the 450,000. Okay, so now I will introduce our major work on the static mapping between the sparse pressure data and the aerodynamic loads. So here we assume there is a linear regression between the pressure information and the aerodynamic load as shown here. So this is the aerodynamic load measured by the pressure sensor. And we got the 15 or 14 pressure tapes on the dot wing. So we got the pressure data in the time sequence. And for this work, we want to get the coefficient to build the linear regression between the aerodynamic load and the pressure data. So for this job, also we just want to minimize the cross function here. So in this way, we can determine all the coefficients here and just get the load reconstruction here. And with this job, we can also find some critical spacing, or critical location of the pressure sensors on the dot wing. And then it gave us some valuable insights on how to reduce the number of the sensors here and how to optimize the location of the sensor. So, and for this job, we focus on the dot wing. So here is the two examples of how the flow over the dot wing. So the left example is for the 20 degree angle of attack. The right column is the 30 degree angle of attack. As you can see, for the 20 degree angle of attack, so there are very strong leading vortex over the dot wing. But for the 30 degree angle of attack, so due to the vortex burst at the leading edge, so there is no strong flow structures over the dot wing. So basically for our experiment, so the dot wing moves with this inertial condition, and it's either in the vertical gust or in the transverse, it's either in the vertical gust or in the axial gust. Okay, first, let me introduce the results about the axial gust. So in this case, the dot wing first have a constant speed about 1 meter per second, and then it accelerated to 1.5 meter per second. And right now, I just showed the results for the G star equals to 1 and G star equals 2. So as you can see from this figure shows what's the steady aerodynamic load for the dot wing for the 20 degree angle of attack. So we can say there is a stall between the 20 degree and the 30 degree. So basically for our experiment, the dot wing already close to the stall situation for the 20 degree angle of attack, but the flow over the dot wing is fully separated for the 30 degree angle of attack. For the 20 degree angle of attack, we can see that the linear regression works well, and it gets pretty close results to the aerodynamic measured by the force sensor. And we can see at the beginning of the gust, there is a very sharp increase of the lift coefficient. That corresponds to a strong leading edge formed over the dot wing. And for the 30 degree angle of attack, we can also find a very sharp increase for the lift coefficient. That means even the initial condition is the fully separated flow, the axial gust motion can induce a very strong leading edge vortex and get a very strong lift increase over the dot wing. And something seems bad news is that for the drag coefficient, the linear regression cannot do a very good job. You can see there are very large fluctuations for the drag predicted by the linear regression. One possible explanation for this is that for our experiment, we only use the pressure sensor. We don't have the shear stress sensor. So that means for the drag coefficient, so maybe it's not accuracy to estimate the drag coefficient. In future, maybe we can just add some shear stress sensor to improve the accuracy. And for the vertical gust here, so actually we use a linear actuator to drive a vertical acceleration profile like this. And for the vertical gust, the maximum effective angle of attack will approach 11 degrees for when the for the h star equals 0.5. If the h star equals 0.25, the effective angle of attack will approach 5 degrees. So that means for the initial condition, if the angle of attack is 10 degrees, so the maximum effective angle of attack will become 20, and that will approach the edge of the stall. And if the initial angle of attack is 30 degrees, and for the maximum effective angle of attack during the gust, the angle of attack will become 40 degrees. That is a very large value, but we can see that even at this case, we can find a very large lift. We can even find some large lift here. That means the vertical gust can also induce the leading vortex, and that leading vortex can provide some lift over the dot wing. And we can also find some bad news for the drag coefficient. We can also find very large fluctuation for the drag coefficient. So yes, this may be the same reasons we don't have the shear stress. So basically the drag prediction is not as good as the lift prediction. And another part of this job is try to find the try to optimize the pressure location on the dot wing. And this part of job is related to the regularization. So during our regression case, we actually minimize the cross function here. And this cross function actually includes two parts. For the first part, it describes the difference between the measured value and the regression estimation. So that's the reason why we need to minimize the cross function. So that means we can make our prediction close to the measured value. But and another part of the cross section is the lasso regularization. So the reason we want to introduce this part is we want to reduce the magnitude of the coefficient in the regression. For example, if we don't have the this part, the lasso regularization, so the prediction will become something like this. We will have very large fluctuation for the estimation. So we basically call this situation overfitting. If we increase the lambda here, actually we enforce the magnitude, we reduce the magnitude of the coefficient in this way. Then we can move our prediction something like this. And here the line is basically smooth. It doesn't have very large fluctuation. So we basically assume this is a good fit. But if we continue to increase the lambda, we can get a very low accuracy of the prediction. It is something called underfitting. It's also another case that we want to avoid. So basically we need to choose a reasonable lambda to get a very good prediction. And here is the results on how we can use the regularization to reduce the number of the sensors. So for this plot here, so the x-axis is the magnitude of lambda, and the blue lines is the error between our regression estimate and the measured value, and the red lines is the number of the non-zero coefficient. So if we increase the lambda, we can say that the error of the regression becomes larger. But at the same time, the number of the non-zero coefficient decreased with the increase of the lambda. And this case, this situation basically same for both the axial guts and the vertical guts. And in this case, we prefer to choose the lambda at 2. In that case, the error didn't increase too much compared to the small lambda case. But in that case, we actually have smaller number for the non-zero coefficient. For this case, we have only 9 non-zero coefficients for the linear regression. That means for the other, we actually reduce the 5 pressure sensors for the dot wing. So those pressure sensors doesn't provide any information into the linear regression. So in that case, we reduce the number of the sensors. And we also need to check whether the reduction of the pressure sensor can provide better linear independence of the linear regression. So here we use this parameter, variation inflator factors, the VF, to estimate whether the estimator is linear independent from the others. So basically, if the VF below 10, we'll assume that the estimator is linear independent from other estimators. So for example, for here, we just increase the lambda from left to right, as we can see. If we increase the lambda, the non-zero coefficient on the dot wing becomes less and less. First, we have basically 15 non-zero coefficients on the dot wing, but finally, we only have 4 non-zero coefficients on the dot wing. And the VF values for lambda equals 2, in this case, basically below 10. That means the left 10 pressure sensors are basically linear independent. So we can use them as the fundamental basis for the load estimation. This is the case for the axial guts. For the vertical guts, we can find the same thing. If we increase the lambda, the non-zero coefficient becomes less and less. First, we have 15 pressure and 15 non-zero coefficient over the dot wing. And finally, we only have 4 non-zero coefficients over the dot wing. So basically, for our case, we prefer to choose lambda equals to 2. In this case, we can get good prediction for the linear regression, but we can also reduce the number of sensors from 15 to 9. So in that case, it will save money in the practical application. Okay, and next I will introduce our work on the neural network modeling for the dynamic separation. So our project focused on non-slender dot wing. And for the slender dot wing, people already developed some theoretical analysis about the aerodynamic loads. And they are shown here. For the theoretical analysis, the aerodynamic loads include 2 parts. The first part is from the potential theory, the KP atom, and another part is from the vortex lift, so which shown as the KV atoms here. So under the KP and the KV actually is a function of the aspect ratio of the dot wing. So, but those equations works well for the slender dot wing, but actually they doesn't work for the non-slender dot wing, especially at high angle of attack, as shown here. So for this part, the dark line is the experiment, is our experiment on our non-standard dot wing. And the red line is the prediction from the theory. As you can see, at the small angle of attack, so basically the results from our experiment agree with the theory. But if we increase the angle of attack, actually the difference becomes larger and larger. That predicts aerodynamic loads for the non-slender dart wing at a high angle of attack. So this is something has to be addressed. So we want to use a neural network to correct those equations and get very good prediction for the lift and drag. And the reason why the current theory doesn't work for the non-slender dart wing is the complex flow structure of the dart wing. As shown for here, at 20 degrees, we got the leading vortex here. But we can see after some pounds, the vortex burst, and we don't have very strong vortices here. So that means basically the vortex lift theory doesn't work after this pound. And for the 30-degree angle of attack, the situation is even bad, even worse. So as you can see here, so the vortex burst happens at the leading edge. So we cannot observe obvious flow structure over the dart wing. So that's the reason why the current theory cannot provide good estimation on the aerodynamic loads over the non-slender dart wing. So here we want to make some correction for the current theory. So we introduce this item to estimate the flow separation over the dart wing. For this case, we use F as the attachment degree. So for the fully attachment flow, where F equals 1, the lift coefficient is equals to the current theory. But when the separation point reaches the leading edge, the F equals to 0, and the lift coefficient is just 1/4 of the lift predicted by the theory. So in that case, we add this parameter to our model. And here, the follow image shows the flow separation during the gust. Okay, so here is a vertical gust case, and we have 20 and 30-degree angle of attack here. As you can see, for the 20-degree angle of attack, the flow separation first decrease and then increase back to 0.4. But for the high angle attack case, the attachment degree keeps constant between 0 and 0.1. So that means for the 30-degree case, the dart wing basically fully experience fully stall during the gust. And in our neural network modeling, so we want to get a mapping between the pressure signal and this attachment degree. So here is the results. So for our neural network model, so for the input layer, we use the pressure signal from the surface of the dart wing. And finally, for the output layer, so we use the attachment degree. And if we got the attachment degree, and we can get back into this equation, and finally solve the lift coefficient here. And this is the results we got, our final results we got from the network modeling. As we can see, basically the measurement lift coefficient agree with the prediction from the neural network, where basically this result is pretty good. And for the comparison, we can see from the linear regression, for the 30-degree angle of attack, there is a obvious difference between the measurement value and the estimation from the linear regression. So from here, we can see that the neural network did a much better job than the linear regression. But there is also drawbacks for the neural network. So for the advantage of the neural network, it can simulate any continuous function in this world, at least if the neural network include one hidden layer and use nonlinear activations there. So if the neural network meets this condition. It can simulate any function in the world. So that's a very obvious advantage. But it also have very obvious drawbacks here. So first, we need a lot of data here. So basically, it's not who has the best algorithm that wins. It's either who has the most data that wins. So that means for the neural network, we need a lot of data there. But for our experiment, so it's very expensive to collect data. So basically, that's some very huge drawbacks for the neural network used by the experiment data. And another drawback of the neural network is that it lack of physical understanding. So for the neural network, it doesn't understand the Newton's second law, and it doesn't understand why the density cannot be negative. So basically, we cannot get very good physical insights from the neural network. So basically, from those 2 points, we design some future job that will solve the above 2 drawbacks and get better model for our experimental data. Okay, so for the first part of the future work, we want to try to estimate the aerodynamic for the multiple types of guts. For our current case, we only care about the axial guts or the vertical guts as shown here. But actually, there are so many types of guts in the world, and people already did some studies there. So for the most of the application, the people care about the random guts like this. So there is random velocity fluctuation during the gust. So for the next stage of our work, we try to test our model for all kinds of different gusts and try to see whether this data can provide better modeling for the gust control. So another major direction for our next step is we want to get some network model that relates the pressure network to the vortex topologies. For example, so for here, this is a dark green. We have very strong leading vortex here, and it have very strong 3D flow structure. So we want to get a mapping between the sparse pressure signal and the vortex topologies. That's the next step of our research. So, and for the transverse guts, we modeled by the pure plunge. Actually, we have to acknowledge that. So the pure plunge is not the perfect transverse guts. And our group had did some modeling before by this guy, and he found that if we want to model the transverse guts, actually we need a very complex motion, which includes a pitching motion, plunge motion, and the surging motion. So it's very complex motion here. But for our vertical gust case here, so the reduced frequency is basically about 0.63. And from this modeling, we can know that if the reduced frequency below 0.5, so the accuracy will increase to 90%. That means the motion is pretty close to the transverse gust. But for our case, the K is below them 0.75. That means the accuracy of the pure plunge to the transverse gust is only 80%. So this is a good simulation, but it's not perfect. So for our next job is we want to improve the accuracy from 85% to 100% by using very complex motion. This motion is just a combination of the pitching, plunge, and surging. In this way, we can simulate the actual gust in the real world, and we can. And the further job is not only the vertical gust. Maybe as described before, we we can do some simulation. We can do some work on the random guts. And another work is how to get the connection between the surface pressure and the vortex structure over the dot wing. So those results compare the connection between the pressure gradient on the dot wing and the vortex structures over the dot wing. As you can see, for the 20-degree angle of attack, so we have very strong leading vortex here. And we can see there is also strong span-wise pressure gradient here. So that means there is strong connection between the pressure information and the flow structure. And for the 30-degree, we can find the same thing. So for here, the flow structure is not obvious because of the vortex burst. And for the pressure signal, we can find that the pressure gradient is small. And basically the information from the pressure distribution is not as obvious as the low angle of attack case. That also give us some idea that the flow structure is highly related to the pressure distribution. So in that way, for the next step, we want to build a network model between the sparse network on the dot wing and the flow structure on the over the dot wing. So maybe this part of job is too difficult for us to conduct. So, and we want to use some reduced order model instead. For this case, we don't reconstruct the full 3D flow over dot wing, but we just reconstruct some major information of the flow, something like the position of the vortex line and the strength of the vortex over the dot wing. So for here, this is detail. So if we have the dot wing, we can find that this is vortex line. So at the beginning, the vortex line is along with the leading edge, but at some point we got the vortex tilting, and the vortex line changed the direction. So basically, we care about the 7 parameter scale. The first 3 are the position of the vortex tilting. That is the location of the spatial location of the where the vortex tilting happens. And another important parameter is the circular feeding rate. It's how the circulation increase from the peak to the vortex tilting point. And after this point, the direction of the vortex line is also important for us to reconstruct the aerodynamic loads. And so finally, we care about those 7 parameters, and we want to get the neural network between the pressure signal and those 7 parameters to build the modeling. And another part of job is about the transition network approach that will be introduced by the Frieder on May 12th. So hope guys can also be interested in this direction. And they use the transition model to get some reduced order model of the flow, and look at the information from the phase space. Okay, so now I just make some conclusions. So first thing is that, so from our research, we found that the static mapping actually can get some good fitting between the pressure information and the aerodynamic load. And the lasso regularization we use in this study actually provides some valuable insight into the sense reduction. And from the lasso regression, we can get also some information on how to optimize the pressure sensor over the dot wing. For the future job, first thing we want to use neural network and other advanced model to predict the unsteady aerodynamic loads from the pressure signal. And another thing is that we want to build a mapping between the flow structure and the pressure data over the dot wing. So I stopped here and welcome any comments and suggestions on our research.
Yes, thanks, Wenchao, for the nice talk. Okay, any questions from the audience?
Hi, Wenchao. I have a question.
Okay.
This is Shai. Can you hear me? It's good. It's good to see you again. So
Yeah.
it's very good talk and it's very interesting. And I have a question. And you mentioned that you used a neural network to approximate the load, aerodynamic load, and there's no physical constraints, and it requires lots of data, right? So my question is this: is it possible to use a physics-informed neural network? That means that you use the neural network to approximate the aerodynamic load, and at the same time you you compute the loss function using the differential operator, and you minimize the loss function so that you will have physical constraints. Will this get better results? And of course, this will require less data.
Yeah.
Do you think this helps to get better results?
Yeah, I guess so, but maybe there is also some challenges there because for the experiment data, we have large noise there. So we don't know whether the noise level can influence the prediction performance of the neural network. So basically, for all the results published, they just the simulation work. So basically, no noise in this work out, and sometimes they will add some noise manually into the model, and just check what's the influence, what's the effect of the noise on the model. But actually, it's an unknown question. So because few people have applied this model to the experiment data. So that's something challenging. So yeah, and another thing we care about is we want to get some flow structure from the neural network. So that means the cost function has nothing to do with the physical understanding, but the output layers. But for the output results, it can provide us some physical information. So in that case, so the first step is get a mapping between the pressure and the flow structure. And the second step is get the force from the flow structure. So there are two steps. So maybe this way is more practical because the first step, we assure that people already published the paper on that. They confirm that this way does work. And then we just fill the second step, how to get the aerodynamic load from the flow structure. So for that part, we already have the flow dynamic information, flow dynamic knowledge about that. So this part is also practical. So in that case, it's more practical to apply. But if we use some hidden physical neural network, it is unknown. So we are not sure that this way does the job. So maybe that's something even future. So yeah. But currently we don't. I guess it's too risky for us, and we want to get some practical method first. So hopefully I can answer your question well. Yeah.
Okay. In fact, it's a theoretical thought because the PIM involves the differential equations, the governing differential equations, which is the physics. So you have physical constraints. So maybe it's a question you can try, or
it's something we can try, but it's risky, as I said. So maybe it's something even future. So it's not something we need to do it in a short time. It's it's a future plan. First thing, right now we just focus on the traditional neural network, and basically we have some idea that it should work anyway. So that's something we need to start.
Okay, thanks for your answer.
All right, thank you.
Anyone else? So Ming Tai, you can go ahead.
Okay, I have two questions. So, so for the pressure data, so you are using pressure tabs, right? So what's
Yes.
the pressure value? It's a gauge pressure or it's an absolute pressure?
So we have one absolute pressure sensor, and for the other ones, they are just differential pressure sensors. Yes, so that's basically that configuration. Yeah.
Okay, so the second question is you don't put a pressure sensor or pressure tabs on the back of the delta wing, right? So you only, so my question is for the vertical gust, maybe the gust won't affect the pressure underneath the wing, but in axial gust, the flow or the wing will affect the pressure underneath the wing. So did you consider about that?
So basically, only cares the pressure distribution on the suction side of the duct wing. So for the other side of duct wing, we didn't collect any pressure data there. So yet it does has some influence on the pressure measurement, but from the experiment, I guess the influence is small. It's not a strong effect on the pressure distribution on the other side of the duct wing.
Yeah, but if you see if the delta wing is tilted 20 degree and 30 degree on the side of where the pressure taps installed are in the separation zone, you know, which means the pressure data will be inaccurate to predict the aerodynamic forces. So the bottom surface is facing it's facing to the gust, you know, in axial gust.
Yeah.
Do you understand my point?
Yeah, you mean so it will have some trailing edge vortex, and maybe that vortex can move forward and get back to the move to the surface where we measure the pressure distribution, right? So something like that. So yeah, it is possible, yeah. But right now, from our experiment, so the trailing edge vortex is small. We don't find very strong flow from one side of the duct wing to another side. So maybe if we try some stronger gust, yes, that effect is more obvious. But for the current experiment, so we cannot very find strong reverse flow over the duct wing. So basically the flow is just along the streamwise direction. No flow get back over the duct wing. So.
Okay, thank you very much.
Any more questions?
Yeah, so Wenchao, I actually just follow up like a main test question. So I just want to confirm that right now you're only accelerating the axial, like the gust is, you're basically starting at 1 meter per second and accelerated to 1.5 meter per second. You don't deaccelerate like in the case, right?
Yeah.
So yeah, so if it's like mainly it's accelerating, then the high pressure section, like well, maybe not like facing like any detached vortex and all the things. But if you're deaccelerating, then maybe the trailing edge and like a leading edge vortex will be rolled up into the like you can say belly section. We may force like some very interesting phenomena later into like modeling. So.
Yeah. So right now we only have the acceleration gust case. So we didn't see any obvious reverse flow or something. So maybe it's not an issue here, but we have some plan for the deceleration gust. So maybe that's some issue in future and we need to care about that. Yeah.
So actually, I have a very technical question. So I have also been using some pressure sensor. So pressure sensor a lot of times is notoriously for its noise ratio. So the sensor to the information to noise ratio is pretty high. So
Yeah,
do you
yeah.
see that in your experiment? And if so, how did you mitigate that?
Okay, so that's something indeed challenge, and we also found that there is a large noise for the signal, but we just fell onto the high component part during the experiment. So, but yes, that's a very good question, and that's something we need to care. So actually, we are trying to buy more sensors with smaller range. So that means we can get much better signal to noise level. So yes, right now we found that our pressure sensor, maybe the range is a little bit too large for the value we measured. So that will result some very large noise. But for the next plan, we are already just ordered more sensors. They will come in 2 or 3 weeks. So they have smaller range. So it will give us better resolution for the data. Yeah. That's indeed something difficult. Yeah.
Yeah, thanks. I mean, I know how difficult to play with pressure sensors.
Yeah.
Thank you. So,
any more questions? Wenchao, could you go to page 21?
Okay.
So I just have a question about the model. Will this kind of CL has any kind of memory effect on the basically depending on alpha? So meaning it's not just depending on the instantaneous value of alpha, but angle of attack but also on the history of the angle of attack.
So what? So sorry, I cannot understand your question. So
sorry. I mean, yeah. Go ahead.
So you mean the attachment degree actually has a history information, right?
Yeah.
So,
yeah. That's my question.
That's true. Yeah.
Mm-hmm. And is that important or not?
So actually, that also gave us some insights on how flow separation in the time sequence. Maybe during the vertical gas, maybe the flow separation have some its traces. Yeah. So yeah, so it all I guess it's maybe it offers us some information how the flow involved during the gas. Yeah, that means the angle of attack is not enough. So we need some history information to predict the aerodynamic load. That is true. Yeah.
I see. Okay. And last question is basically it's very cool. Basically, you use the data from several locations to estimate the integration, basically the total load. Is this possible that we can make a prediction of the whole flow field? I mean the whole pressure field on the wing surface, because
that's something we're aiming for. We hope so. We hope it can do the job, but maybe it's not. So that's just some ambitious plan actually. Yeah. So actually we want to get some loops there, so we can use a neural network to estimate aerodynamic load from the pressure signal. But we can also do another way. We can use some fluid dynamic theory to predict the pressure distribution from the flow flow structures, right? So in this way, we can generate a loop there. So we can from the pressure data to the flow structure, and from the flow structure to the pressure data with the knowledge of the fluid dynamics.
Oh, yeah.
Yeah. Cool. So if we have this kind of loop, we can just go on, and finally we can maybe all the data convert to some situation. In that case, we can just use the pressure data to predict the 3D flow over the dot wing, and that can give us some good estimation of the pressure distribution on the dot wing worthly. So that's something we hope to get, but it's some ambitious plan. Maybe it's not work. Yeah, that's some preliminary plan for our future job. Yeah.
Yeah, very interesting. Looking forward to that. All right, I guess it's last chance for the audience to ask questions. If not, we will end. Any more questions? All right, let's thank Dr. Wenchao Yang again for his nice talk.
Okay, thank you.
And we will end here. Okay, see you guys.
Okay, see you.